Torque, 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 torque. So, torque. We are going to talk about torque. Torque we define as that, which we define as a sum. So we talk about torque around a point, and we define it as a sum of positions cross product with forces. So what does that mean? Well, if we have some object which, let's say, is fixed around an axis of rotation, so it could rotate around here, so it's there, spins around. And what we would do if we wanted to find the torque on this object is we would go to different locations on it and see what forces are being applied, and we take the position vector from the axis of rotation to the point where force is being applied and cross product it with that force. So let's say there's a little person over here who's applying a force. We would do R cross F would give us a torque vector, which, using the right hand rule, would be going in that direction, would give us a vector. And similarly, if there was another person over here who was perhaps pushing a force in another direction, then we would add these up to find a total torque, and if that was unbalanced when we added it up all across the object, then the object would start to twist. It would its spinning motion would be altered. Torque acts very much like forces do, but in a sort of twisty way. So we have Newton's laws, which we're familiar with already, for pushing and pulling things. When, in the absence of forces, an object keeps moving in the same direction and at the same speed. Similarly, in the absence of torques, an object keeps spinning in the same way at the same speed. We have the familiar force is mass times acceleration, position coordinate second derivative, which is also a vector. Similarly, we have torque is something called the moment of inertia times the angular acceleration. That's supposed to be theta. There we go. Which is also a vector. And Newton's third law, we have for every torque there's an equal and opposite torque happening. So when you when there's a merry-go-round and you're pushing the merry-go-round to make it go round faster, what you're really doing is applying a torque to the merry-go-round, and if that torque is large, then you get a large angular acceleration and it starts spinning faster and faster and faster. So why do we care about this r-coordinate? Why is this r-coordinate important? Well, we already intuitively know that it's not just forces when we're trying to twist something, because we know about levers. We're familiar with levers. If you've ever opened a paint can, which maybe looks a bit like this, you have a lid and it's got a little lip like that. This is quite a bad drawing. There we go. There's our lip. And if you want to open a paint can, you usually use a screwdriver or something like that. Here's our paint. So you use a screwdriver to pop open the lid. Now you could, when you have the screwdriver here, you could push down here to try pop open the lid. But you don't, you always push down at the end, and because it's easier. It's simpler if you push down at the end to pop open the thing. And why is that the case? Well, it was noticed long time ago by an ancient Greek dude called Archimedes, and it's called Archimedes' law of levers. And what he noticed was that when you have a really long lever, it's easier to push things and lift things and things like that if you have a big long lever. And it's related to this concept called torque. So if we have a pivot point, a fixed pivot point, and let's say a balance beam on top of it. So this is balancing. And we put down, say about here, a couple of bags of sugar. Now these bags of sugar have a weight that's pressing down, and that weight is like a force here, and it's at a distance from this pivot point, so it's applying a torque to the balance beam, making it go like this. And if we want to balance it, then we need to apply another torque, an equal torque going in the other direction. And we could do that just by putting 2 bags of sugar here at the same distance. However, what you'll find if you set something up like this at home, which you could easily do, is you could balance them with just 1 bag of sugar by putting the bag of sugar further away. And in fact, if you test it, use a ruler or something, you'll find that 2 bags of sugar, a distance of say 20 centimeters away from the pivot, can be balanced by 1 bag of sugar 40 centimeters away. And there's this linear relationship to do with them that you can visualize using this concept, this idea called torque. And indeed, conceivably, if you had a really, really long balance beam, you could put a really heavy weight here and put a really light weight far away, and they would balance each other. And this is what led to Archimedes' famous quote, "Give me a lever long enough and I will move the world." If his idea being, you have a little pivot there, if you have a really, really long lever, then me on the end could lift something as heavy as the entire world. And I am not. I'm quite skinny. I am quite a skinny gentleman. I think that's me almost done. So in summary, torques work very much like forces, but they're just a twisty version of forces, and all of the ideas that we're familiar with Newton's equations, they have their equivalents in twisty version. Force turns to torque. Your angular acceleration will turn into your linear acceleration will turn into angular acceleration. Your mass turns into moment of inertia. Your linear momentum turns into angular momentum. And indeed, there's an equivalent of collisions and things like that you can talk about. So, final theoretical question. Why is it, to see how you're thinking, why is it that when you're going uphill on a bicycle, it's very hard to go uphill on a bicycle when you're in a high gear, and very easy, or easier, when you're in a very low gear? And it's to do with this concept called torque. See you next time.